and then PhD in artificial intelligence. He's done some work on modeling cognitive functions, but he's worked on these methods for learning abstract concepts by sucking them out of the data is what, of course, continues to amaze us. His work shows what you can do with great intuition in mathematics and infinite faith that the secret of the brain is a simple formula and you can find it. So, thanks, Jeff.
Thank you. So what I'm going to talk about today is I'm going to spend about the first 10 or 15 minutes talking about a basic model for how you learn layers of features. As you all know, pattern recognition consists of getting some features and then putting weights on the features to make a decision. And people spend a long time putting weights on the features to make a decision, but they never tell you where the features come from. And backpropagation was one idea about where you get them, but it didn't work very well. And we've got a much better idea about how to get features now. And because it's Johns Hopkins, I'll conclude that section with a little example of trying to do speech recognition. Then I'll show you why, even though this works pretty well, it's not quite what you want, and there's a much better kind of basic module. So the idea is we're going to have a module that's going to learn features, and then we're going to learn features of features and features of features, and every time we learn more features of features, it's going to get better. But the basic module, we're going to make a bit more general now, a bit more powerful. I'm going to show you how that more powerful module can learn how images transform over time. It can learn how people walk in different styles, and it can learn to model images by creating a covariance matrix on the fly that's specific for each particular image. So it has like a gazillion possible covariance matrices that it synthesizes out of basis functions for each image. And that leads to much better modeling of images and image recognition. And right at the end, I'll say that once you've learned to do vision like this, then speech is sort of trivial. You just pretend it's a vision problem on the log spectrogram, and you turn this loose on, and it just does much better than the speech people. That's to be provocative. Okay, there's a model introduced by Paul Smolensky in 1986 that he called the harmonium. I didn't like the term harmonium, so I called it a restricted Boltzmann machine. And at the time, I thought it was it's a rather simple model with no connections between hidden units, so it's not really interesting because we've got the general learning algorithm with connections between hidden units. And why should you bother to run the general learning algorithm in such an impoverished machine? And I can now answer that question. So this is Paul's model, and it's going to turn out that if you want to learn layers of features one at a time, this is the right thing to use, or a right thing to use. This little network only has connections between hidden units and visible units. I'm going to talk in terms of images mainly, so think of visible units as like binary pixels, and hidden units as stochastic binary feature detectors. And if you know the weights on the connections, which are symmetric, then given a visible vector, that is an image, the probability of turning on each hidden unit is the logistic function, that is 1 over 1 plus e to the minus x, where this is the x, of the total input that that hidden unit gets from the visible units, that is the states times the weights on the connections. Similarly, when you go the other way around, given a hidden vector, h, the probability of turning on each visible unit is the logistic function of the total input that that visible unit gets from the states of the hidden units times the weights on the connections. Okay, so simple conditional probabilities. And a very nice inference property, which is that given an image, the feature detectors are all independent. So it makes it very easy to activate the feature detectors. Much easier than in a directed model where you get explaining away and all sorts of mess like that. This network is governed by an energy function, a sort of Hopfield energy or quadratic energy, where you take the state of each visible unit, which might be 1 or 0, the state of each hidden unit, which is 1 or 0, and if they're both 1s, you add in the weight between them, and if it's a big positive weight, that gives you negative energy, which makes the network happy. So a network's very happy when it has pairs of visible and hidden units active that have big positive weights between them. This has a nice simple derivative with respect to the weight, which is just the product of these two activities. And so when we want to do learning, we want to manipulate the energy by manipulating the weights so that the data is probable. We also want to manipulate it so what the model already believed becomes less probable. And so you'll see this showing up lots of times because that's the derivative of the energy function with respect to a weight. you can define the joint probability of a visible and a hidden vector in terms of this energy function. It's just e to the minus joint energy, normalized by that same quantity, I could have put a v and h here, summed over all possible combinations of a visible vector and a hidden vector. And since there's exponentially many of those and exponentially many of those, it's hard to compute this. Even worse, if you want the probability of a visible vector, you have to sum this over all possible hidden vectors that might go with it, and there's exponentially many of those. So that's the probability of a visible vector. And in order to make visible vectors more probable by changing the weights, we ought to change the weights so that the energy of this visible vector, together with whatever hidden vector it would like to go with, goes down, and the energies of all other pairs of visible and hidden vectors, particularly the ones that happen a lot, go up. Okay? You want to make the bottom line smaller and the top line bigger to make this bigger. So it turns out the nice thing about these networks, which Terry Sinofsky and I figured out a long time ago in 1983, is that the learning algorithm is very simple. It's particularly simple in this simple structure that Paul came up with, which is that given the visible units, you activate the hidden units stochastically. That is, you compute p of hj given v for each of these things, and then you sample from that p. So it might be a 1 or a 0, but it's stochastic. Given this binary vector, you reconstruct the image. So again, you sample from the probabilities that these guys define, and you get another binary image. And you just keep going like that until you've forgotten where you started. And then you're sampling from what the model really believes in. So with this undirected model with symmetric connections, to see what the model believes after you've learned is not trivial. You have to go backwards and forwards a long time, and now you're seeing examples of the kinds of things the model believes in. That is, you're seeing the low energy states of the system, and you're seeing them with a probability that's proportional to e to the minus the energy. The learning algorithm, however, is nice and simple. You measure statistics, that is, you measure here how often a pixel I and a feature detector j are active at the same time when I'm showing it data. So I use 0 to indicate the start of this chain. You measure the same thing when the model is just fantasizing, and that difference tells you how to change the weight to improve the log probability. And it's quite remarkable it's that simple, because how you should change this weight depends on all the other weights. And where are they? Well, it turns out they show up in this statistics. It's not like backpropagation where you explicitly take them into account. They just show up in the statistic. And so it's a difference of two locally available things. If it was a synapse between V and H, it's the difference between two things that are both available at the synapse. So that made Terry Sinofsky and I quite excited. Unfortunately, you have to run for quite a long time to get fantasies from the model, and you're not quite sure how long. So I made it go 1,000,000 times faster. And the way you make it go 1,000,000, I discovered this by accident. The way you make it go 1,000,000 times, or actually by being lazy, the way you make it go 1,000,000 times faster is instead of going all the way to equilibrium, you just go up and down and up again. And you measure statistics there and statistics there. Now that's no longer, this difference is no longer the derivative of the log probability of the data. But it's good enough for learning in all sorts of models. And it's actually very close to being the derivative of something else that's quite sensible that I won't go into. It's not even the derivative of this other thing, but very close. Now, you may think, well, how did that make it 1,000,000 times faster? Because, you know, we used to run this chain for 100 steps, and now we run it for sort of 1 step. But it took me 17 years to think of this, and in that time, computers went 10,000 times faster. So the longer it takes you to think of an idea, the better it is. Now, the reason this module's interesting is not sort of so much for the module in itself. It's because if you learn a layer of hidden features like this, then there's good reasons why, if you take those feature vectors that you got from data and you treat them as data and do it again, you'll get a better model. In fact, I can guarantee you that if you initialize the weights right for the second layer, namely you make them equal to the weights you already had for the first layer, then when you start learning those second layer weights, the overall composite model you get will be better than the model you already had. And I'd like to guarantee you the same if you do a third layer, but I can't. But what I can guarantee you is this, that there's a variational bound on how good your log prob is for the data. And if you keep learning, if you were to do the maximum likelihood learning where you run the chain for a long time, if you keep learning, every time you add a layer, that variational bound will improve. You'll get a better bound on the log prob of the data. and that's good enough for me. So given that I've got this thing that keeps improving as we add a layer, we then violate all the conditions of the proof, and we just get on with it and learn lots of layers of features. And we show that they work really nicely for doing stuff. After you've learned a lot of layers of features, what you've done now is from data with no labels, just looking at the data like images or spectrograms or something like that, you've learned lots of layers of nonlinear features. And you did this with no label information. After you've done all that, you've designed your features now, and now you can associate categories with the last layer of features. So you stick some labels on the end, learn the weights from the last layer of features to the labels, and then you can backpropagate to fine-tune the features. But the fine-tuning of the features isn't discovering features. It's just ever so slightly changing them to move the category boundaries around. So maybe the boundary between 4s and 9s wasn't quite right. And if you look at these feature vectors, when you do the fine-tuning, they change by sort of at most 1% typically. Very small changes. So the key is, don't use the information you have in the labels, which is precious, to design features. Features have lots of parameters, and you can design those just to be a good model of the data, the input data. And the input data is very rich structured, so you can design lots of features on not much data. Then use your labels to ever so slightly fine-tune things to be good for discrimination, and you'll do much better. And Yoshio Bengio, using his brother's computers at Google, ran lots and lots of simulations to show that if you take a feed-forward neural network, you can put in random weights and train it on labeled data, or you can learn layers of features this way, and then add the categories at the end, and then train it starting from there. And if you train it starting from there, it works much better, it gives much better discrimination, and what's more, you're in a completely different part of weight space from what you get to if you start with small random weights. So, it's obviously the right thing to do. And here's the sort of, this is the most important take-home message of this talk, this is the sort of ideology. If images were generated by taking stuff in the world and creating an image, and then taking the image and creating a label, then the right way to associate labels with images would be to try and learn this mapping. And that's what most machine learning has tried to do. But you don't really believe that. I mean, that would be true if the label is things like the top right-hand pixel is on, or the parity of the pixels is odd. Then the label wouldn't depend on this stuff, given that you knew the image. But it's not like that at all. What you believe is that the stuff, oh, incidentally, this is a technical concept that comes from Donald Rumsfeld. The stuff, and it gives rise to images, and that's a very high bandwidth path. It's so high bandwidth that just looking at the image you can figure out what the stuff was, if you've got a good model. And then the stuff also gives rise to labels. Like maybe your mother says cow. But if you consider the label cow, it doesn't tell you how big it is, where it is, whether it's alive or dead, what colour it is, anything, whether it's a happy cow, none of that. Whereas if you look at the image, you can tell most of those things, because this pathway is so high bandwidth you can invert it. So now if you want to associate the label cow with images, like you're looking through a window and there's a field and there's this little brown dot and your mother says cow, you're much better off first inverting this pathway to find out what was really going on in the world, and then associating what was really going on in the world, or some representation of it, with a label. And that's sort of what we're trying to do when we learn these multi-layer nets unsupervised. Get to here and then do this. But then as a final stage, slightly fine-tune this inverter so you get better labels. But that's a very minor effect. Now, so far I had binary units. I actually want to operate on things with real values. So we'll slightly change the rules. We'll have a different kind of variable for the observables. They won't be binary pixels, they'll be real valued pixels now. And so we change the energy function to look like that, which looks more complicated. But notice this is the kind of VIHJ term. It's just the activities of the visible units have been scaled by their standard deviation. So we're measuring them in z-scores, which seems like the right thing to do. And we've added this extra confinement term. This says that a visible unit is very unhappy if it's a long way away from its bias. Notice there's a plus there, so it's unhappy. Whereas there's a minus here, so correlations there make things happy. So you can think of there being a parabolic containment function, which says that a visible unit likes to be around here, which is its learned bias, and as you move away it gets unhappy. That's what stops it all blowing up. As many of you know, a parabola is the negative log of a Gaussian. So this is really just a linear variable with Gaussian noise, and that's its log prop, negative log prop. Now if you ask what effect do the hidden units have on a visible unit, then if you differentiate this term with respect to the activity of a visible unit, you get hj, wij, this sum scaled by that. And that sum is therefore the slope of this line. And so the top-down effect is like a sloping line that says it's lower energy out this way if the hidden units would like you to be on, and it's lower energy out this way if they'd like you to be off. And eventually, the gradient of this equals the gradient of that, and that's where you'd like to be most. The effect of that top-down input from the hidden units is to just move this parabola over. The gradient plus a parabola is just a moved over parabola. So conditional on the hidden units, the linear unit is just has a Gaussian distribution, but with its mean moved over by the hidden units. So that's the model with linear units. And that was tough to understand, and you didn't really need to understand that. Just think of it, it works for binary units and it works for linear units too. So now let's try some little example. There's something called the TIMIT database, which is for recognizing speech. There's a classification task which is relatively easy and a recognition task. In the recognition task, I give you a few frames of the speech, and you have to tell me what phone you think the middle frame was. Actually a probability distribution across phones. And actually you've modeled each phone already with a three-state hidden Markov model, so you have to tell me which phone and which state of its hidden Markov model. There's 61 phones and 3 states, that's 183 phone states it might be. And you give me a distribution across 183 phone states. And then there's post-processing, that in our case just uses a biphone model, that takes those distributions, figures out what the most plausible sequence of phones is, but collapsing them down to 39 categories, and then tells you where the phoneme boundaries are, and then compares with a transcription, a hand-labeled transcription, and says how often you got the phone right. So this is what the real speech recognition people are interested in, because you're not being told where the phoneme boundaries are. You have to come up with distributions that are good enough to find those boundaries. Okay. And so you get the phone error rates out of your post-processing. So now you can divide the sort of phoneme recognition task into, can you give me a good distribution? And then does your post-processing do something sensible with it? So I had a very good master's student who's just finished his master's, and he believed what I said about adding layers of features. He believed it much more than I did, actually. And so he took the standard representation of frames of speech. He took 11 frames with a 10 millisecond advance and used 13 Mel-Capitol coefficients and their differences, temporal differences and temporal differences of differences, which is the standard representation. And then he learned 2,000 binary features that looked at these guys. And then he did it again, and I'd kind of stopped there. But I was away. So then he did it again, and he did it again. And then he thought, I'd better have a narrow layer. And the reason I better have a narrow layer is all of these green things are trained unsupervised. So you can train them to sensible values without any label information. But the very last layer here, these red guys, going to the right answers, have to be trained supervised. You need to know something about what the right answers are there. And so you want a small number there so there aren't too many of these. You don't want more than a few tens of thousands of those. But notice there's 4 million here and 4 million there and 4 million there. I mean, we're rather profligate with the parameters. So he trained it all up and then back-propagated through everything. And he got 23% phone error rate, speaker independent. And at that point, the record was 24.4% speaker independent. And the 24.4% was done by averaging lots of models together. And this just kind of worked. So that's my example of a sort of vanilla application of this approach. And it's nice because he used a bizarre number of hidden layers. Later on he tried more hidden layers and it worked slightly better. Now, these numbers don't have to be right. If you use 2 hidden layers of 2,000, you'll get between 23 and 24%. And if you use 1,000 in a layer, you'll get between 23 and 24%. If you do more or less anything plausible, you'll get between 23 and 24%. And that's more interesting than the fact you get 23% with the best architecture. Any old thing gives you better than this. Okay. You have to do it on a GPU board because this takes like a day or two to train on a GPU board and would take a month or 2 on a core. So the new idea is that that kind of network, which just has pairwise connections, is flawed because it can't deal with multiplies. And to get really good generative models of stuff, you need multiplies. And I'm falling behind, so I'll tell you why. Suppose I wanted to generate a square, and I wanted to generate it from something that said it's a square and said its size and shape, size and orientation and position. Well, I could have very accurate information that tells me where the parts are, and then they come out in the right relations. Or I could have sloppy information that tells me, given that it's this, and given that it's this pose, roughly where each part is. And I might even have redundant parts. And so that's meant to illustrate a distribution. And you could sample from these distributions, and then you get something that was a very raggedy square. Or you could do something else. You could download at the top, same time as you're saying where the parts should be, you could say how they should relate to one another. And actually that's what these temporal differences are doing in your speech representation. You don't know the capsular coefficients. Your model can't predict those very accurately, but it can predict the relations between them much more accurately. So here what we're going to do is we're going to download a sort of Markov random field that says how parts go together. And then given that Markov random field, we're going to take this mess and clean it up and get that. Now if we cleaned it up again, we might get something that was a slightly rotated square, or slightly bigger, but it'll be a nice clean square. And my analogy for this is if you want a bunch of soldiers to stand in a rectangle, you could take your GPS and you say soldier number 1, and you give him like 7 coordinates and say stand there. And soldier number 2, and you give him seven not coordinates, but 7 precision, 2 coordinates with 7 digits of precision. And you'd have to make it very precise to get a reasonable rectangle, right? Or you could say soldier number 1 stand over there somewhere, and then you could say soldier number 2 stand this far away, and then you'll get a nice neat rectangle, maybe in slightly the wrong place, but it'll look nice and neat, with very little information conveyed. Okay. That's because you can convey the MRF in one command by saying like that. Which, if you had basis functions for MRFs, might be just fine. You say which MRF to use. So that's why I want a more complex module where the hidden variables don't just determine the probabilities of the visibles turning on, they determine interactions between the visibles. Okay, so to do that we need higher order Boltzmann machines, where instead of this kind of model, you have 3-way interactions. So this might be a hidden unit, this might be 2 visible units, and this 3-way weight says, if hidden unit k is on, then have this weight between these 2 visible units. If hidden unit k is off, that weight's not there, because this is all going to be a 0. Okay. Now, that means that a hidden unit can download a whole bunch of pairwise interactions, and that's good. On the other hand, this has 3 indices, and if we have n of those and n of those and n of those, we've got n cubed of these parameters now, and that's bad. But let's stay with the bad for a minute, and let's try modeling transformations of images. So here's an image, and maybe we had binary pixels. And maybe what we're doing is just translating pixels. So we translate these pixels, and maybe this one goes here and this one goes there. And what we'd like to do is learn that that's a consistent transformation, and learn sort of what the name of that translation is. It's this translation here. And so we could do that if we learned a big positive weight 3-way weight here and a big positive 3-way weight there. So that when we see this guy, when we see that guy and that guy, via that big positive weight, that says this, you'll win if you turn this guy on. And this pair also says you'll win if you turn this guy on. And that'll overcome his bias, so it'll turn on. And if these pixels went somewhere else, well, we have another guy for that. So you can see how we could learn, if we could learn this stuff effectively, we could learn what the translation was that took this into that. But we've got these n cubed parameters here, an awful lot of them. And actually, if you think how images transform, these n cubed parameters would allow us to learn arbitrary permutations of the pixels. And that's just what images don't do, right? Images do very regular things. There's a lot of things, but they're sort of typically affine transformations of some kind. Maybe different affine transformations in different places, because you've got 2 objects. We can handle that just fine. But they're not arbitrary permutations. So that gives you the idea, maybe we can have this model, but we can factorize these so we have far fewer parameters. We'll have the multiplicative interactions, but we'll somehow try and make do with less parameters. So, that was our model with 3-way interactions, where that's a hidden and these are 2 visibles. And we're going to say, I'm going to model this weight by saying I have a whole bunch of factors, and for each factor, I'll have 3 one-dimensional things. This only has, for factor f, this only has that one index I. And so if we have about n factors, then we've only got 3n squared of these guys. So that seems like good news. Obviously, if we have enough factors, we can model anything here. But with a reasonable number, what we can model is some kind of reduced set, which will turn out to be ones that have nice regular structure. Another way of looking at it is, we wanted this 3-dimensional tensor of weights, Wij, and so we have, for a factor f, we can think of this 1-dimensional vector of weights and this 1-dimensional vector of weights, take that outer product, and you have a matrix that only has rank 1 here. And then these guys are just scaled versions of that matrix, so the whole tensor only has rank 1. And we've got a tensor made out of 3 one-dimensional things, and by adding up enough tensors like that, we can get anything we like. But maybe by adding up a relatively small number, only about n of them, we can get the things we need. But what does inference look like in this model? Well, if you ask, what does hidden unit H need to know in order to choose one of its 2 binary states, the one that's lower energy? Well, it needs to know how the energy function changes as it changes state. The derivative of the energy function with respect to its state. And that turns out to be the following. Take this factor. The factor has this sort of 1-dimensional set of weights to pixels of the pre-image. So let's stay with the motion case. The pre-image, the post-image. Take these weights, multiply the pixels by the weights, and that'll give us a sum at this vertex. Do the same here, we'll get a sum at this vertex. Multiply those 2 sums together and send it to this hidden unit, multiplying by this weight on the way, and that's what this guy needs to know. You see, the whole energy function is the product of these 3 sums, but the derivative with respect to the state of this guy is the product of these 2 sums and that weight. So now we've got it down to pairwise interactions. No 3-way interactions anymore. You compute this filter, you compute this filter, you multiply them together, and you send the result there, multiplying by the weight on the way. That's called belief propagation. One thing to notice is this isn't like a stochastic binary unit. If you put a stochastic unit in here, it will correlate all these guys and inference would be a pig. This is a deterministic factor, and it keeps these guys independent given the data. So it makes inference nice and easy. It also makes learning nice and easy. So the message that the factor sent to the hidden unit was the product of the 2 sums at the lower vertices. It was the product of this thing and this thing. And to learn the weight from the factor to the hidden unit, what you want to do is, when you're showing it data, you want to compute the derivative of the energy with respect to the weight, and then you want to sample from the model, or at least reconstruct the data and sample from reconstructions, and compute the same derivative, and take the difference of those 2 derivatives. And the derivative of the energy contributed by factor f with respect to this weight is just the product of the state of the unit H and the message that gets sent to it from the factor. So again, it's a pairwise product of this message and this state. And you've got this nice simple learning algorithm in terms of pairwise things.
Can you quickly clarify something? Maybe it's a notation that's confusing me. So I indexes the...
Oh, I use terrible notation.
In the pre-image, let's say. J indexes the
Yes.
the post-image. So they could run over the same index set.
Then they'd be the same image.
They're the same image, like the same image space, if you will, if it's an n by an image.
Right, but we're going to keep I for the pre-image and J for the post-image now, and later we're going to do what you say.
Right, but then WIF and WJF don't refer to the same weight.
They don't have to be the same, no. Different weights, as you will see.
Okay.
Right. So I use this silly notation where the index tells you which set it's an index over. I is the typical pixel of the pre-image, and J is the typical pixel of the post-image. Okay, so what we could...
How do you deal with the fact that the pairwise weights are only defined after scale? Because the triple-wise weight is the product of the 3, so you could scale the first by a factor and divide the second by a factor, and then there is...
Very good. You do a bit of regularization. So if you put a bit of decay on all of them, then it'll tend to keep them all about the same size. Or we tried all sorts of things, like taking that factor out explicitly, because we thought it would make the learning better, and turns out it didn't. But yes, very good point. So a bit of regularization will stop it blowing up. So we're going to take images of dot patterns, we're going to translate them, and the translation is going to have an arbitrary direction and an arbitrary distance, but small. And then we're going to learn by following that derivative, and we're going to look at the weights that connect a factor to the pre-image and the weights that connect to the post-image. And we're going to display the weights in a little picture like this, where these are the weights to the various pixels in the pre-image, and these are the weights to the various pixels in the post-image. And because we're doing translations on dot patterns, we'd like to see the Fourier basis just learn. Okay. So if you take 100 factors, these are the 100, each of these is a factor, and these are its weights to the pre-image. So it learns to be a little grating filter. It looks for energy at a particular phase, well, not energy, it looks for a particular phase and a particular frequency and a particular orientation. And you see it's covered the range of orientations and frequencies and phases. If you look at the weights to the post-image, they look like this. Pre-image, post-image, pre-image, post-image. It's learned the same grating but in quadrature, basically. And that's a very good way to represent motion. Mathematicians will tell you that's the right thing to do for translations. You can give it rotations, and then it learns a bunch of pre-filters that look like that. See, it's got yin and yang here, and it's got the radiation symbol here. You might wonder what the next term in this sequence is from yin and yang and the radiation symbol, and I'll tell you in a minute. Things are getting bad. So the pre-image, post-image, pre-image, post-image. So these are a good basis set for rotations. The graduate student who did this was German, and it took us forever to find one that didn't have any swastikas on. Okay. Now, we trained it on 10% dense dot patterns that were just translating, but it was always the same translation. But it's learned a distributed representation for these translations. So what would happen if you were to give it 5% dense dot patterns, but 2 of them, and they're moving in different directions? Okay, and it's never seen that before. That's transparent motion. And most people who extract motion from images, you give them transparent motion and their method breaks down, because they have some explicit parameters saying what the affine is in this patch and so on. And they don't like having multiple affines in the same patch. Here, this was the very first time we'd ever saw transparent motion. It was suggested by a vision guy. He said, what'll it do for that? So we tried it. And in order to see what it was thinking, I mean, it's all unsupervised, this, right? There's no labels anywhere, so how do you know what it's thinking? Well, we learned the layer of hidden units, and then on top of that, just using ordinary binary units without the three-way interactions, we learned a very sparse layer. So we learned a big layer of units and forced them to be sparse. And those units learn to be very tuned to particular orientations. Each unit is tuned to just one orientation. So now you can look at a pattern there, and you can see if it's all the units are tuned to roughly the same orientation, or if you can see if there's a bunch tuned to this orientation and a bunch tuned to that orientation. And if you see that, you say it's got a sort of multimodal percept. It's seeing 2 different motions at the same time. So now when you show it this transparent motion, is that within about 30 degrees, it sees one mode at the average. That is, the average of the 2 directions is the thing that's most active, and it's one mode around that. If it's beyond about 30 degrees, you get 2 bumps, and what's more, they're slightly repelled. That's exactly what people see, and that proves that this is exactly how the brain works. Okay, now I'm going to do time series models. People try and do inference in directed time series models using dynamic Bayes nets if they're brave. They're quite hard to fit to data. But it's hard to do inference, so most of the time people use one of 2 models, which are the most complex models you can do where inference is trivial. You can use a hidden Markov model, or you can use a linear dynamical system. The hidden Markov model has local state in the sense that when you generate data, each frame is generated by one node. You don't get a bunch of things conspiring to produce a frame. And therefore you can't handle data in which there's several different things going on in the data. You can't handle it efficiently. A linear dynamical system has a bunch of things going on in the hidden state, but they've got a linear relation to the data. So you can't handle nonlinear stuff. So you can use a mixture of linear dynamical systems, but that's not very efficient. Alternatively, you can use something with simple inference and fast approximate learning and much more powerful representations. And what you lose on the fact that learning is only approximate, and is more than made up for by the fact you've got a very powerful model. So we're going to take the previous model, a restricted Boltzmann machine. We're going to have visible units that are linear units with Gaussian noise. We're going to have binary stochastic hidden units. And now we're going to condition on previous frames of data, previous observed frames. So again, there's no connections between hidden units, which is what makes inference simple. Since these are all linear, then these blue connections are an autoregressive model. The prediction of these linear variables from these guys is just these guys times some weight matrices, plus some biases. So that's an autoregressive model. And that's very good for smooth motion. It's not very good when you get discontinuities. So we're going to use it for modeling walking. And when your heel hits the ground, things change very differently from how they did a moment before when your heel was in the air. A shock wave goes up your leg, and autoregressive models don't like that kind of thing. So we've got these binary variables. We'll have hundreds of them. And what they'll learn to do is override the autoregressive model when weird nonlinear things happen. But we'll get the advantage of the autoregressive model taking out all the simple linear structure for us. So we don't waste these on modeling linear structure. It's very easy to learn. You simply, given these previous frames, you initialize that at the data. You activate these guys, they're all independent given the data. Then you reconstruct these guys, given the top-down effect coming from there, and the effect coming from the autoregressive model. And then having reconstructed them, you activate those guys again. And then you use the difference in correlations here with data and with reconstruction to learn these weights. You use the difference in activity of these guys with the data and with reconstruction times the activity of these guys to learn these weights. And similarly, the difference in activity here in data and in reconstruction times the activity of this guy here to learn the weight on this connection. So the learning algorithm's basically the same. Once you've learned, you can generate from the model. So given these previous frames, we can initialize these guys at random, and then we can go backwards and forwards 30 times or so. And this will settle to equilibrium quite quickly, because given this previous stuff, and given that it's fairly smooth data, there's not much freedom here. It's stochastic, but it can't go to crazy places. So you can get to equilibrium quite fast there, conditionally on this. So that's how we could generate from the model. And once we've learned this model, we can play our stacking game. Because once we've learned that model, we figured out how to transform visible frames with linear variables into hidden frames. Once we've done that, we can make a better model by taking this as data and learning a model of that using more binary units. And to generate from this model, we go, given these two, we go backwards and forwards here, and then given what we get there, we just go chunk and use these as well to activate something there. Alternatively, we could use three-way connections, and that's what I'm going to show you.
A quick question though, going back to the previous slide. If the hidden units in the first learning stage do actually try to capture, let's say, the nonlinearity of the transitional parts of the signal, non-smooth, why do you expect there to be a useful AR model in the second layer at all? I mean, wouldn't that just...
Well, you expect that over time, for example, maybe when my foot hits the ground, things go wobbly for several frames.
Okay, so in other words, the smoothness may be more local.
Right.
Still some
Yeah.
smoothness.
Yeah, and in fact there is, because this model works better than the one-layer model. So, we're going to model motion capture data, and so what you do is you put markers on the joints, you have infrared cameras, the infrared cameras say where the joints are in space, you then do some math and figure out what the joint angles are, and then you have frames that consist of joint angles plus the translation and rotation of the base of the spine. So now you can imagine a little mannequin, a little wooden mannequin, stick a pin in the base of his spine, and the way we're going to make him move is by going like this with the pin and following out a trajectory. That's the variables that say the translations and rotations. And as we do that, he's going to wave his legs in free space, and if he waves his legs just right, it's going to look like his foot's stuck to the ground and he's walking. Okay? If he waves his legs in a way that's not precisely coordinated with how we move the base of his spine around, then his feet are going to appear to skid on the ground. So we've got a very simple perceptual test of whether we're doing this accurately when we generate. How much do his feet skid?
It's almost like a puppeteer trying to make the puppet.
We're a puppet, yes.
Robotic.
It's the Boltzmann puppeteer, right. But we're going to use a three-way model. So we're going to take the current frame of joint angles and translations and rotations. We're going to take 6 earlier frames. We're going to condition on those. But this autoregressive model, instead of being a normal autoregressive model, is going to be actually a blend of a whole bunch of autoregressive models. You can think of each one of these factors as a kind of rank 1 autoregressive model. And then we're going to know what style the person's walking in. That's a 1 of n. We're going to learn to transform that into 100 real valued features of style. So we can have styles that are similar to each other. And then these 100 real values are going to be the input to this vertex. And so you can think of each of these as like one of our previous hidden units. Each of these will have weights to several of these factors. And we'll sort of synthesize out of these rank 1 matrices a little autoregressive model. But now we have exponentially many, actually it's a continuous space of them, but if these were binary, we'd have exponentially many autoregressive models that we could synthesize. Much more powerful than, say, a mixture of autoregressive models. And we just train the whole thing up in exactly the way I said before, which may not be immediately obvious, but it all flows from what I said before, if you think about it long enough. And so now we can sort of see what it generates after you've learned. So we're going to train it on lots of data from one person walking in different styles, and then try generating in those styles. So here's his normal walk being generated. Well, I've got Vista, so who knows? Okay, there he is. So this is generated by the model. And you see the feet do skid on the ground slightly, but not too badly.
So you are putting the pin in the base of the spine, but that's the only...
No, it's generating that too, though.
It's generating the fact that you're working the circle too, so this is completely free.
Completely free running. But the point about thinking of the pin is that it has, if it didn't coordinate the translations and the leg waving, you'd see foot skate.
Yes, I understand. If you wanted to push it in a particular direction, you could just absorb some units and have it in front of the others.
Very good. You can draw a path on the ground, and you just sort of regress him slightly towards that path on each frame. And then you can direct him where to go. And there's advanced versions of this where you can tell him how fast to walk and all sorts of other things. You can have more than just a global style variable. You can have lots of little style variables about speed of walking and foot stride length and all that stuff. We can get him to walk like a gangly teenager. Now this is exactly the same autoregressive models, but they're being blended differently. We can get him to walk like this. Cease to be research now. This is fun, okay? We can get him to walk like a drunk. He's good at that. Now remember, this doesn't have a physical model, so the only reason it can stumble and recover is there had to be things a bit like that in the training data. We can get him to walk like a cat, softly. What's interesting is there's the same sort of blend of autoregressive models, but they're going much slower now, and he can stop and start again. Autoregressive models can't do that very easily. An autoregressive model has a biggest eigenvalue that's either bigger than 1 or smaller than 1. If it's bigger than 1, it blows up. If it's smaller than 1, it just dies. And so what you do is you get the biggest eigenvalue just below 1, and then you keep driving it with noise, and then it'll stay alive. And that's like trying to make a dead horse walk by jiggling it. Okay, we can get him to a graceful walk. He's a computer science student, I think, so he's only seen C3PO. That's the only graceful thing he's seen. And we can get him to do a sexy walk, but you probably wouldn't be interested in that. We'll actually switch the label to normal at some point. And because it's all one model with different styles, he can do the transition even though he's never seen a transition. And probably what was happening with Memento wasn't quite right during the transition. But I'll bet you it was almost right. And as far as I know, this is from a learned model, this is the best generation you can get. You can get better generation from an accurate physical model, but that involves huge amounts of integration and things. That really understands what's going on properly in terms of physics. This is just learned from the data.
These labels are supervised or they're unsupervised?
This is supervised in the sense that we were telling it the label for the training data. Since then, what we've done is we've taken stuff without labels and use this for tracking, where you have a particle filter and you use this as your prior knowledge of motion. So you train this up on lots of data, unlabeled, and then you can use a mixture of these models. So in effect it's learning to break up the data into different styles, and that works really nicely. It gives you much better tracking than if you use a dumber prior. It's by far the best prior that people have used for tracking, as far as I know.
Okay.
Yeah.
So for that to lead that, you have explicit description of the state, with velocity, acceleration, all that?
In this stuff,
Yeah.
it's just joint angles you're giving it. Frames of joint angles that it's generating.
You get them like, if you want velocity or acceleration.
Yeah. Right.
Another question, this sort of, I guess, speculative question. If you took the same setup as before with the walking data, but instead of giving it the 1 of n encoding for style as an input, if you just train that as yet another hidden layer, is the expectation
That's what I was.
you would,
Yes, that's what I was saying. For tracking,
yeah.
in effect, that's what we did. We learned those different styles. Right. Okay. So one more thing we could do is we could just say, let's take 2 copies of the same image, so that if I equals j, wif equals wjf. In other words, I've drawn it like this, so it looks like what we're doing already. But it's really just, we've got a factor, it's just a linear filter on the image, and you square its output. So the rules are, learn a linear filter, you square its output and send it to the hidden units. That turns out to be a very standard model in vision. That's the oriented energy model. And it's used by both biologists and computer scientists, one of the few. And biologists have tried measuring what the exponent is on this linear filter. And Yang Dan at, or Dan Yang, well, I think she's called Yang Dan at Berkeley, has says the data says the exponent is between 1.7 and 2.3, which is really nice, right? Because you know what's between 1.7 and 2.3. So we derived this model. I didn't expect to come up with this standard model. I just started with a 3-way energy function and tried to make it work by factorizing it, and it gives rise to the same model. But the big advantage is, because we derived it as a generative model, we now have a nice simple learning algorithm for everything. We can use the sort of Boltzmann learning algorithm for everything. And what we're going to do is we're going to try and learn it so that hidden units are modeling covariances between pixels. And one way of thinking why that's a good idea is this. Suppose I ask you, what is a vertical edge? Well, most people will say a vertical edge is where it's dark this side and light that side. Or maybe it's dark this side and light that side. And so you say, well, haha, what about if it's light here and dark there and dark here and light there? Is that an edge? Well, yeah, that's an edge too. Oh, what about if it's a stereo disparity, or a texture edge, or a velocity edge? And most people say, okay, so there's a whole lot of kinds of edge. But they all have one thing in common, which is a vertical edge is an instruction not to do horizontal interpolation. If you've got a vertical edge, you can interpolate this way, you can interpolate that way, but you mustn't interpolate this way. So what we could do is we could have a hidden unit that says do horizontal interpolation, and so we believe in that smoothness, and then when we see that horizontal interpolation isn't working in the image, we turn off that hidden unit, say don't do horizontal interpolation. And so now the state of that hidden unit is representing the covariant structure of the image, not just the means. And that's a much more powerful thing to represent. If you think about what you know about most images, and suppose you could know roughly what the mean is for each pixel, but with some noise, or you could know whether these 2 pixels have very similar values at a much more precise level. You'd much rather know which pixels are the same as which other pixels than what the actual values are. It's what's the same as what that's really meaningful. That's covariance structure. Now, once you've got these hidden units that are representing covariances between pixels, then given the hidden units, it's not easy to do a reconstruction because you've got these things that aren't independent anymore. When we conditioned, earlier on we were doing conditional models, we conditioned on this and reconstructed that. That's easy because given this and this, these are all independent. But just given this, and the fact that these have to be identical, now you're in trouble. So we use a different method for doing the reconstructions called hybrid Monte Carlo, where what you do is you start at the data, you look at the derivative of the energy function, and then you track along that derivative for a bit. And you just wander along it for 20 steps, and then you say, okay, that's my reconstruction. It's not at equilibrium, but it's towards equilibrium, and that's good enough for the learning to work. So that's called hybrid Monte Carlo, that method, and I'm not going to go into it anymore. Once you've done that, the learning is just the same. So the learning algorithm is the same, it's just we generated reconstructions using hybrid Monte Carlo. And so what we're going to do now is we're going to have one set of hidden units that models means, and gets the rough means of the pixels, which is what most models do. So sort of dynamically, the states of these hidden units are making a bet about the mean. And then another set of hidden units that dynamically is producing a precision matrix, an inverse covariance matrix, and making bets about the covariances. And then we model a data point, and most models model a data point as a noisy version of this mean that they synthesized from the states of the basis functions or hidden variables. We're going to model it as a noisy version of a full covariance Gaussian, where some units specified the mean and many more units specified the covariance, but we've synthesized up a covariance matrix specially for that image. So here's an example. Here's an image, a 16 by 16 patch of image. Here's the noiseless reconstruction of it from our model after it's learned. Here's the stochastic reconstruction. You see it reconstructs very well. So what we're going to do is extract the covariance matrix from that image, our dynamic representation of the covariance matrix that's appropriate for that image, and extract the means, and then we're going to throw away the means, and we're going to lie to it about the means. We're going to say, for example, the mean values of the pixels in this image are they're all uniform grey except for these ones which are darker. And then we're going to say, take this crazy information about the means and try and reconcile it with what you believe about the covariances. So, for example, you believe pixels in here have to have the same value, and pixels in here have to have roughly the same value. And I'm telling you this pixel is very different from those ones and very different from those ones. Well, you know it could be different from those ones but you think it should be the same as those ones. So when you do the reconciliation between the covariance structure and the mean structure, you get this. It blurs that this way. And if you simply put in 4 blobs of colour like this, or 4 blobs of lightness, you get this, which looks pretty like the original image. And that's showing you that really crummy information about the means, plus the right covariance structure, gives you a similar looking image. Therefore, similarity for us is better conveyed by the covariance structure than by the mean structure. Notice if I actually reverse these, and do that, I get the opposite image, which actually also looks quite similar because it's sort of got the same shape. Okay. So now what we do is we take patches of colour images, 16 by 16. When I say we, I mean my postdoc Marco Aurelio Ranzato, and learn basis functions for the means and basis functions for the precisions. And the basis functions for the means learn this. They learn sort of cloudy things without any sharp edges. But if you add together some subset of about a third of those guys, you can get any colour wash you like over the image. But it'll be a sort of colour wash. It'll be like in watercolour, you know, you sort of do a sort of wash. But if you put in sharp edges too, then the wash gets slaved to the sharp edges and you see something sensible. So this is just like for doing the colour wash. What about the precision units? What do they learn? So I'm going to show you what these factors learn. And they learn to look like that. So there's a lot of factors, it's overcomplete, and it's on colour images. And some of them learn to be low frequency, red, green or yellow, blue edge detectors. And most of them learn to be almost exactly grey level. That is to plot, when I plotted this, when Marco Aurelio plotted this, what he did was to plot each pixel in there, he takes the weight that this factor has to the blue channel, the weight to the green channel, and the weight to the red channel, and plots it in that colour. So the fact that it comes out grey says that it's learned to make those weights exactly equal, which is kind of interesting. It decides on real colour image patches, most of your filters and all your high frequency ones should be uncoloured. Even though this is coming from cones, that is, it's coming from red, green, blue guys. There's something in the data that says do that. I think what it is that if you look at my cheek or a crease on my cheek, for example, it's the same material, and lighting normally doesn't change colour much with direction. So there's no colour contrast. There's an intensity contrast, but no colour contrast. And a large fraction of the edges you see are like that. So you'd want a lot of things with no colour contrast, and then when there is a colour contrast, you just add in some of these guys and you're at your colour contrast. But what's interesting is that looks just like a piece of monkey cortex. It has these topographic things. It has this colour blob of low-frequency colour detectors, and they're red, green, and yellow-blue. I think they're like that in the monkey. And most neuroscientists would say, well, that's got to be innate. This just emerged from the interaction of a sensible learning algorithm, factorised three-way weights, very rich data with lots of interesting structure, and one more thing that made the topographic map, which was some local connectivity. So the net was actually connected like this. The pixels to factors was global, so the fact that they were local receptor fields, it learned that. But then we laid out the factors in 2D, we laid out the covariance hidden units in 2D, and we had local fields connecting one of these guys to the factors. And for reasons I don't have time to go into, that caused it to form a topographic map. This is a trick due to Arpa-Hovarainen. This is an example of things generated from the model. And with the exception of a model by Mike Lewicki and Jan Karklin, as far as I know, nobody can generate sensible-looking patches of colour images. When they generate it, either it looks like little gratings, or it looks like clouds, or it just doesn't look right. Here, when you generate from this model, that is, like we did for the walking, this is sort of completely unconstrained. You just ask, what do you believe? It believes stuff like that, and the data is stuff like that. And you'll see it believes in long straight edges. It believes in, look, there's some texture here, and some parallel straight edges there. There's sort of even a corner there. It's not quite right, and it tends to generate too many smooth patches, but we're getting there. This doesn't have the property that it looks cloud-like, which most things do. It has the property images are mostly smooth with sudden eruptions of structure. And that's because we're modelling this covariance stuff. We can apply it to supervised learning. I've got about 3 or 4 minutes to go. So this is a real object recognition task where you take millions of images from the web and then we hand labeled a subset. And that's what aeroplanes look like. And this is what birds look like. So this is a view you don't want to have of an ostrich. They're very varied, right? Much harder than normal object recognition tasks. And we've only got 50,000 labeled examples, 5,000 of each class. But we have millions of unlabeled images. So we can train up this covariance model on unlabeled images, and then if we like we can train another layer or more layers on unlabeled images, and then finally stick the labels on the top. We could then backpropagate, but we didn't bother. We just wanted to see how good the features are, even if you don't fine-tune them. Mark Aurelio, who did this, came from Jan LeCun's lab. So if you don't watch him very carefully, he does convolutional things. So he actually learned 8 by 8 image patches, and then stepped them across the image like this. But he learned them with these 144 hidden for representing the covariance structure and 81 for the mean. And then there were 49 patches in the image, the 32 by 32 image. And so that gave 11,000 hidden units. And then what we did was we tried to associate classes with those 11,000 binary hidden units. Actually with their probabilities of being on. So if you take the pixels and do multinomial logistic regression on the pixels, you get 36% right. If you take some features developed by Toralba at MIT, but not very many of them, you get 54%. If you take a normal RBM with binary hidden units, Gaussian visible units, you get 60% correct. If you take this thing with units for the means, units for modeling covariances, and a lot of these factors, more factors than actually hidden units, you get almost 70%. And if you then add an extra layer of hidden units, you do even better. And that's the best result so far on this database. But it's a fairly young database. But it really works twice as well as just looking at the pixels.
How long was for the training?
Yes. Because he was only doing 8x8 patches, and because he was doing it on a GPU board, that would train sort of in overnight or faster. He's now got the code more efficient, and the code he's putting on the web, so you can train on 10,000 examples if you've got a GPU board in 10 minutes. Then there wasn't any fine-tuning here, so basically overnight.
But how large is the training set?
He used, he actually didn't use enough. I think he was meant to use 2 million images and all the patches from those, so it'd be hundreds of millions of patches. He actually ended up only using a few 100,000 little patches. They're only 8x8 patches. He's now doing it with bigger patches and using more. But ideally, you'd like to learn on lots and lots of data so you get a really good model. And the key is it doesn't need to be labeled. So we can learn on data that has covariance structure in it now. So why not go back to the speech recognition problem? And instead of using the Mel-Kepstrel representation, which is a standard one, let's just use log spectrograms. That's sort of cochlear pixels. I don't know much about speech, but it turns out you don't need to. You just pretend it's vision, and you take what comes out the cochlea, and you make a little window of it, and then you just try and treat it as a vision problem. So there's a guy called Victor Zhu at MIT who's quite good at this, but he uses lots of context in a complicated language model, and he can get about 15% error, but using this other stuff. So we used 40 filter bank coefficients, well, the DC plus 39 others, to be like the Mel-Kepstrel. 1,000 precision units and 576 mean units. And then he added 4 more layers of 1,000 binary units because he likes 4 layers. In fact, later on, 7 layers worked even better. What was impressive was the very first time he tried it, he broke the record for speaker-independent phoneme recognition, what the record was at the time, we thought. And then when he added a few more frames, he gets down to this, which is very good for speaker-independent. If you look at the sort of history of Timit, and this is my last slide, back in the 80s, recurrent backprop got 26.1% correct per phone error rate. The record before we started this deep learning stuff was 24.4. We've now got it down to 21.7 speaker independent. But at the same time, the IBM speech group have gone back to Timit, and they've taken everything they learned from doing big vocabulary speech recognition, and everything they learned in the last 20 years since people did Timit, and they can get also 21.7% correct. It turns out to be exactly the same. But we're using a biphone model, and they're using a triphone model, and they agree that's worth about 0.5%. And they're using vocal tract length normalization, and they agree that's worth about 0.5%. And then they told me some other trick they're using. Oh, they're collapsing to 48 categories, and we're using the 61 categories, and they say that's worth about 0.5%. And what's more, they know much more about speech than we do. This is one master student who doesn't know much. So they're smart and we're stupid, so we should have another 3 or 4% for that. So look, there's where the record was before. Here's human performance. We're about 1/3 of the way to it. So with 2 more ideas, we'll be done. And I'm finished. Okay, I'm finished. Yeah.
So when you add many layers, you have lots of weights to learn. And
Yep.
one could wonder, why shouldn't I learn all the weights simultaneously?
Because it's much harder.
And so perhaps that would be intractable. And
Yep.
instead you're just doing one at a time.
Right.
So what is the relationship between the solution you obtain and the optimal solution?
Nobody has a clue what the optimal solution is for multi-layer things like this. It's just much too hard. What we do know is if you try and learn them all at once, nothing happens. If you don't make too many of them, you try and learn them all at once, and you do it for a very long time, something will eventually happen. But it's just much easier to learn them one layer at a time.
You have way many variables.
Way many.
So
Why don't we overfit?
what about, why do you get a good fit at all, or why
Okay.
do you overfit, or why
Good.
do you have a lot
So
of problems?
most people in machine learning understand about directed graphical models and supervised discriminative learning. Okay? And throw away all those intuitions. So in particular for discriminative learning, you'd be very surprised if you had, say, a binary decision to make, and you had way more parameters than you had training examples. Because you'd like to think you had, just think information theory, you'd like to have maybe 10 bits per parameter, and in discriminative learning, what's constraining the parameters is not the inputs, it's the outputs. And so for a binary decision task, even if both categories are equally likely, you get 1 bit per training case. So you better have a lot less parameters than training cases. Now suppose you're modeling a rich image. What you're trying to do is model the structure in the image. So each training case, roughly the number of bits it's giving you is about the number of bits it would take to specify that image if you had a good model. So it might be redundant, so they're not all separate. But for many of these images, it would take, say, 100 bits at least to specify the image. And we do have less parameters than the number of images times the number of bits per image. But we have many more parameters than the number of training cases. Yeah.
So in speech and vision, data's cheap, labels are expensive.
Yeah. Roughly. Yeah.
So there's this problem with speech community. We don't know what to do with a million hours.
We do.
Yeah. So have you done experiments where you decrease the amount of labeled data, like kept the amount of unlabeled data the same, to see how performance changes as you learn?
So we've done that not on speech and real vision like this. We've done it on a previous model with this modeling handwritten digits. So little images of handwritten digits. And this behaves very well when you have very little labeled data. So this can take a lot of advantage of a lot more unlabeled data. In Timid, of course, it's all labeled. But if you now gave us, if someone would give us, Timid's I think about 3 hours or something like that. If someone would give us another 100 hours of stuff that had the same distribution as Timid but unlabeled, we'd do much better. And pure discriminative methods wouldn't. Yeah.
So therein lies the rub, of course. You said we have lots of unlabeled data, but none of it's the same distribution as anything else.
Absolutely.
So I can give you tons of speech. It won't be like Timid, but it's speech.
But notice that. Remember the guy who walked in different styles? If you give me a style variable that tells me which distribution it is, and I expand that into some features that describe that distribution, it could be which speaker it is too. You can do speaker dependence like this. And then I learn one model for all of those. I'll still get a lot of transfer, but I'll be able to modulate the model. So if I have a very different distribution, I'll be modulating the model so that it's appropriate for that distribution. So I think you'd still get a big positive transfer if you tell me the name of the database and I put that in as a style variable.
This is a hot area.
I know. Right. So don't tell anybody else that idea.
How important is autocomplete representation in your approach?
It's not sort of essential, but it just seems to help. I should say there's lots of other little tricks that sort of help, most of which we didn't use here. Like you try and make it a bit sparse. It tends to automatically try and make itself sparse, but if you encourage sparsity, in some problems that helps quite a bit, in other problems it doesn't seem to make any difference. But basically, big, overcomplete, somewhat sparse representations are probably going to be the best bet.
Use some magnitude of autocompleteness?
So, let's see. This will actually, one interesting thing is if you make it like 10 times overcomplete, this will still learn sensible filters. It doesn't sort of start repeating the same guy again. But no, I can't. Right. I can wave my hands and say 10, but it's probably within a few orders of magnitude of 10 times overcomplete. Yeah.
You showed some of the features that the model learned for the image patches. Can
Right.
you say anything about the features that are learned for the phone recognition?
Yes. George just sent me a copy of his master's thesis, and someone I was talking to earlier downloaded it, so she's got it. And so she's got the thesis, but I can show you what they look like. So here's, say, 11 frames or 15 frames, I can't remember. And here's the low frequencies, here's the high frequencies. You'll get features that look like this. It'll be sort of positive weights here, and negative weights next to them, and it'll be sort of at all frequencies. So that's saying, well, it's interesting to ask, this is the filter that's used to go into one of these units modeling the precision matrix. And so the question is, what is this modeling? Well, if you think about it, if I have two neighboring times, so this is t minus 1 and this is t, and I have one of these factors, and it's looking with a weight of plus 1 here and a weight of minus 1 there, then if these are the same, it will have no output. It'll be happy. Because these guys only complain. They complain about violations of smoothness. So something like that is modeling smoothness across time. So this guy is modeling smoothness across time if he's got lots of pluses here and lots of minuses next to them in a vertical column. But it's modeling smoothness across time as an interpolator that occasionally breaks down. And so when he gets a big difference here, when this is very different from that, you'll get some big output because you're squaring this. And so he'll say the smoothness across time is broken down. So basically a plosive or something like that will be sudden onset of energy at all frequencies, or sudden offset at all frequencies. So you get guys like that. You get some of these guys just for high frequencies. You get also guys that go this way, that are modeling smoothness across frequency. And these guys that go this way are nearly always, we just looked at it, are nearly always band limited. They're in some region here, they're not the whole damn thing. So it's picking up on sort of, the features will tend to be, not for the plosives, but most of them will be band limited features, so they'll probably be good for detecting speech in noise, because only a few of them will get screwed up if it's band limited noise. It's magic. Yeah. Yeah, no we haven't. My bet is, if you want Gabors, this will learn Gabors, if Gabors are a good idea. But also, typically with Gabors, you want to have orientation and scale and position. So you've already got quite a few parameters here, 4. And now you need to tile a space, and so you can't tile it regularly because you'd have too damn many of them. And so you have to make trade-offs. You have to say, I've already got one at a slightly coarser scale at this orientation roughly here, so I don't want one at a similar scale nearby at a similar orientation. And so this stochastic gradient optimization is very good at spacing them out so they tile the space reasonably for the distribution of data you've got. That's very hard to do when you use these parameterized things and sort of just lay out grids. So I think A, it'll learn more sensible things than Gabors if that's what you need, and B, it'll tile the space nicely in a way you couldn't do by hand, by writing a formula.
Maybe I was asking if you also saw some diagonal structures in speech.
So what you'd...
So far showing the time and frequency, but yeah.
So you'd like to see a little thing like that?
Yeah.
Yeah, it has some of those too. It has those guys. Yeah, we noticed that. Who is it? Where's... Is she here, the one... Okay. Anyway, ask her. It's got these two. We actually displayed them in the order of the magnitudes of the weights, the L2 norm of the weights. And these guys tend to have somewhat smaller L2 norms, so they're down the bottom, but they're there. Sorry.
Is it reasonable to ask your system not only to produce a label, but to produce some kind of certainty measure in that label? Perplexity measure?
It does, because what the output of the phone recognition thing is basically a vector of 183 numbers, and it gives probabilities for each of them that add up to 100, add up to 1. Right.
You've just been assigning labels by taking the one best out of that? Or?
No. In Timit, you have this post-processing model that's doing Viterbi using a biphone model, and you just give it, the nice thing is you give it this stuff, and you take a graduate student who knows about speech and say, I'm going to give you these, you tell me my phone error rate. Right. Timit's nice that way.
Have you tried to do anything related to generation of speech from your model of the
we started off trying to do generation because it was based on... Now, one problem, as you know, with speech is that most of the normal front ends throw away information, like phase information, and so it's hard to regenerate from it. So we messed around a long time with things that didn't throw away information so we could actually regenerate properly. And essentially, we weren't getting very far. And then the graduate student who was meant to be doing generation, I went away and he thought he'd just try Timid. And it just kind of worked. So, and also for machine learning conferences, if you say, I can generate perfect speech, they say, why is that interesting? Whereas if you say, I can recognize just slightly better than the other guy, they say, wow! Not that we can generate speech at all. Right. Yeah. Nothing like that, no. No. What's happened is my graduate students have all got internships at the speech group at Microsoft. And the first thing we're going to do is use it for big vocabulary on Wall Street Journal to see if it works for big vocabulary, because most speech people aren't interested unless you do big vocabulary. And then we can do all sorts of other things, yeah.
So this is a small question, I think. The style variable that you set from the outside for your wanting stick figures, and that you talked about wanting to be set from the outside for dealing with lots of unsupervised speech data. Why can't you just learn that? It's basically some kind of mixture, which is assumed to be constant on every sample.
You could learn it, but it's, if you know it, it's easy just to tell it. I mean, if you've got lots of different databases, why not tell it?
Well, sometimes you might not have lots of different databases.
Yeah.
You might, for example, just have some video and, sometimes the camera.
Yeah, so then you can try learning it.
The person switches to a different mode of lighting.
Yeah. I mean, this stuff is magic, but don't push it too far. So, I mean, eventually, if you have too many of these latent things and they're all interacting and you don't tell it them, it's just the learning is going to get very slow, as you kind of know. It's hard to learn a whole bunch of interacting latent things. Yeah.
So, this is a very crude approximation of things what's happening. But one could think of the first part as some algorithm to get good features, some nonlinear features.
Yep.
And the second part is basically just like relatively standard classification.
Yep.
And so you can think of ensemble methods. You could throw 1,000 square vector machines. Each one of those ends up being a feature detector, and then you average them up to that, and you get a classifier which performs reasonably well. So
But
there's a fairly naive way of generating a way that you don't need to use any kind of codings because it's knowledge to generate features.
right, but this has the advantage that the algorithm is straightforward and naive, but justifying that you improve things as you go to extra layers involves some real math. So that's what you want, right? You want something that's easy to implement, but you can pretend you're clever by doing the real math to justify it. And actually, you justify it for conditions that are quite different from the ones you actually use, like almost all the math you read in machine learning. And one comment about the lots of support vector machines. Support vector machines are very, very primitive in what they can do, because one way of thinking of them, they talk about it as this high-dimensional feature space and learning things in high-dimensional feature space, but there's another sense of feature. And in the other sense of feature, a support vector machine is saying, I'm going to create a feature out of a training case. And the feature is going to be the kernel, where you plug in a test case in the training case and look at the value of the kernel. So that's a feature, right? Where the thing I feed the feature detector is the test case. And the problem with those features is they're global. It can't do things like learn to focus on a little bit of the image. It's very hard to get to do that. You have to do lots of extra work. And so it's really just, a support vector machine is just an old-fashioned perceptron with a clever way of generating features from a kernel, namely every training example is a feature, a clever way of throwing out most of the features, so a good feature selection algorithm, and a clever way of setting the weights. So apart from being clever in all those respects, it's just a perceptron. And what it can't do is have things that focus on different details of what's going on and put them together in multiple nonlinear layers. So there's just absolutely no doubt that in the end this stuff's going to wipe out support vector machines. It's just support vector machines do annoyingly well at almost everything so far. But not at this phoneme recognition. We're better at them there. Yeah.
So here's the nonlinear model that I think people played with back in the 80s, that you were Paul maybe played with, I don't remember, where you use an autoencoder.
Right.
You map the image to itself through a restricted layer, and then you do a hierarchy of this.
Very good. You probably know there's a grad student here doing this. Okay. Anyway, yes, you can do that. And this has some advantages over an autoencoder, particularly if you run that chain a bit longer. Not just up and down and up again, but you do it a bit longer. Or there's a variant of the learning algorithm. So this is actually building a probabilistic model, even if crudely. And that's what justifies being able to add layers and get better. With the autoencoder, you can do it, but you've got no justification you're getting a better model. In fact, the autoencoder isn't really a model at all, because it doesn't have a probabilistic model for the latent variables.
No, this is just following on Joshua's comment
Right.
that this is generating features.
Right. So you...
That's layers of abstraction, all of which would eventually feed into supervised learning.
Yeah, so you could say, hey, let's throw away all of this math and all of this nonsense about graphical models, and let's just stack up autoencoders. I suggested doing that in 1989, and I couldn't make it work very well. Yes. But now Yoshio Benjo can make it work pretty well, but it's not quite as good as doing this. And in particular, if you learn with this model with stochastic binary variables, then when you're doing inference, you actually put the noise in, so you have binary values that stops you conveying too much information through one of these variables. And that makes it work much better. It's a very strong regularizer that limits the capacity of the latent variables. When you do an autoencoder, well, you could add noise to them, but typically people don't.
You could also regularize the weights.
Yeah. You could regularize the weights, or you could add noise to latent variables, but this is somehow more satisfying. And it actually works a bit better. Yoshio Benjo has a big paper comparing and sort of standard autoencoders versus this nearly always works a little bit better, particularly when you have noisy data. So one way of seeing the difference is, let's compare maximum likelihood learning in a restricted Boltzmann machine with an autoencoder. So here's your data, and you're going to run this chain backwards and forwards for a long time to get your negative statistics. So you're going to compare these statistics and these statistics. And let's take one of the input variables and make that be pure noise. Doesn't correlate with anything, but it's very noisy. Okay? An autoencoder is going to try and get the reconstruction, this thing here, to look like the data. So it's going to devote a lot of resources to coding this pure noise. If you just want to balance the fantasies with the data, then you don't care if data A turns into fantasy B, as long as data B turns into fantasy A equally often, or the detailed balanced version of that. So there's no need to try and reconstruct. What you want is the same distribution, not the same very exact thing. And so if you give it a pure noise variable, it will just ignore it. It'll model it by the bias of that variable, and that's the end of it.
Thanks, that's right.
But if you do CD now, you just got them down once, it's sort of halfway between maximum likelihood and autoencoder, and it's more at the autoencoder end. So it will pay attention to this, but not as much as an autoencoder. Okay. We're done, right?